Ankush sir, can you hear me?
Yeah, I can hear you.
Okay, sir. So can you please share your slides? We'll just check if everything is okay or not.
Okay, sure, I'll do. Yeah, can you please confirm my...
Yeah, we can see the slides. You can just scroll through them once on full screen.
Yeah. Is this fine?
Fine, sir. Fine. We'll start in a few minutes.
Okay, thank you. Yeah.
A very good morning to everyone and welcome back to day 3 of second Nano Electronics Users Program Idea to Innovation Familiarization Workshop on Nano and Biomaterials and Devices. I am Harika Tanwar
and I Jawaharlal Ghosh.
Second year PhD students of Center for Nanotechnology will host this session centered on simulation, fabrication and characterization of electronic devices. For everyone's information, this session will be recorded for our internal records. And also, all the participants are advised to check the Inup WhatsApp group for any status updates. The former 2 days of this 3 days workshop, a number of eminent speakers from the institute as well as from outside gave their invaluable insights on the topic such as photonics and spintronics, energy generation and storage, biomaterial and devices and sensors. For today, our distinguished speakers in this session are Dr. Ankush Bagh, an assistant professor from the Department of Electronics and Electrical Engineering, Dr. Roy P. Pali, professor and head of Department of Electronics and Electrical Engineering, and Dr. Ashok Kumar Das Mahapatra, professor in the Department of Chemical Engineering. I welcome you all to this session and acknowledge your valuable presence. The participants can drop their queries in the chat box, which will be taken up by the speakers at the end of the talk. To commence this session, I would like to introduce you all to our first speaker of the day, Dr. Ankush Bagh. An assistant professor in the Department of Electronics and Electrical Engineering, Dr. Ankush Bagh completed his doctoral degree from Indian Institute of Technology, Kharagpur in 2016. He became a part of this institute as an assistant professor in December 2021 and has been contributing through his research work in the field of semiconductor devices. His work focuses on growth, fabrication and modeling of gallium oxide-based power devices such as Schottky barrier diodes and MOSFETs. His efforts are well articulated in his numerous publications as well as his vivacious participations in several conferences in India and overseas. Professor Bagh will be acquainting us on the topic gallium oxide for emerging power and optoelectronics, its fabrication and characterization. Along with this, he will present his recent research towards power device and optoelectronic device development based on the low pressure chemical vapor deposition grown beta gallium oxide. Without further ado, I would like to request Professor Bagh to commence this session.
So, thank you and good morning, all of you. So, can you quickly once again confirm if my slides are visible?
Yes, sir, they are visible.
Okay. Okay, so thank you once again, organizer, for giving me this opportunity to present our work on this gallium oxide materials. So let me take this pointer. So just to introduce the topic, say gallium oxide is an emerging compound semiconductor, unlike elemental semiconductor, which we know that silicon or germanium. So we'll talk about this gallium oxide material and everything in the coming slides. So before we delve into the main topic, so let us try to understand the need of this interdisciplinary research, because I think after attending last 2 days session, I think we do all understand and appreciate that we need interdisciplinary approach for realizing a complete electronic system. Now here you can see like this a complete electronic system. If we look into detail, so we'll find some circuits, and those circuits are perhaps made of different active or passive devices, and eventually they are all made of some different material. Now let us see an example of this interdisciplinary research approach. So if we just take an example of this mobile phone again, which is perhaps the mostly used electronic gadget we are having in modern day. So this electronic system is a complete, this mobile phone is a complete electronic system where we can find typical subsystems such as your this power management IC, then transceiver, then audio codec. So these are all subsystems. Now if we further dig into these subsystems, we will find some circuits. So this is a typical power management or power circuits. So then again further if we move into these circuits, which are essentially made of different passive and active devices, and so there will find these devices. So this is a typical hemmed structure which you can or you may find in your mobile phone. So these are gallium arsenide based hem structure. So finally all this hem structure or everything is made of different materials. So like in this research we should cover all these four categories to eventually come up with some electronic system. But obviously it is not possible for a single individual to go through the all parts of this development. So mostly in this talk I'll confine my research to this materials and device development. So this is the broad outline of today's talk. So initially I'll discuss the material development of this gallium oxide and why this is important for coming power electronics or optoelectronics application, as well as the few devices we could fabricate from these materials. So this first part is on material development, and the next part we'll try to cover on the device development. So these devices are both for your power electronics as well as optoelectronics. So looking into this material development, so our material is a gallium oxide, so which is typically called as ultra wide bandgap semiconductor. Now what is this ultra wide bandgap semiconductor? So as we know, bandgap is the most fundamental parameter of any solid state material because it decides what will be the conductivity. Again, I guess from our basic knowledge, we know that we need semiconductor to fabricate any electronic devices, because in semiconductor we can control the conductivity or electrical conductivity. So that is why we need semiconductor to realize any electronic device, because we need controllability. So then this semiconductor has this typical this band gap. So where we know that we can excite one electron from the valence band to conduction band, where this when we'll excite this electron to conduction band, they can roam around easily and we'll get the conductivity. So now typically if know that all the solid state materials can be categorized in three categories like insulator, semiconductor or conductor. So what is this wide band gap? So then in this wide band gap semiconductor, actually this band gap is very high. So sometime this is a history of this particular material, this gallium oxide, because gallium oxide is not very new material. I guess the first report on gallium oxide you can find in the year 1955 or so. But very recently people can dope it. So this is the most important thing, or you can say that the take home message, because this is a typical oxide material which was earlier treated as an insulator. But very recently, last 15 years or so, so people could dope it. So if we can dope this material, so then we can change the conductivity, or we can modulate the conductivity of this material. So that is why we can put this gallium oxide for electronic application. So this is the thing we people have done recently, and that is why all this interest. And similarly, there are other few material parameters which are coming with this gallium oxide. Unlike your elemental semiconductors such as silicon or germanium, as well as few compound semiconductors such as silicon carbide or gallium nitride. So this pentagon actually shows the different material properties of these semiconductor materials. Like here you can see that we are comparing this gallium oxide, that is orange color, with the silicon, gallium nitride and silicon carbide. And these are the different material properties. So in this pentagon, the 5 corners are representing different 5 properties of this material. So in this figure you can see that compared to other materials, this gallium oxide has very good widest band gap, and that is why it has a very high melting point. Why this melting point is important? Because if we want our device to operate at very high temperature, so then that stability will be decided by this parameter. And other thing, obviously, since it has a very wide band gap, so we can give very high voltage or high electric field, and this device can sustain that voltage. But the demerits, what are the, obviously we will not be able to get everything from a particular material. So what are the demerits for this gallium oxide? This electron mobility and the thermal conductivity. And why these two material parameter is important to get the device or our application? Because this electronic mobility will decide your current. So in that sense, this gallium oxide is performing poorly compared to other materials. Again, this thermal conductivity is another primary parameter to decide any power device material, because you know that when we will operate our power device at very high voltage or high current, so there we can expect this high temperature dissipation, because eventually this is I square R. So we may have a very high temperature device. So that heat should get dissipated very efficiently. Otherwise, we may burn our device. So these are the few material parameters. Along with that, so here we have tabulated few other material parameters. So importantly, this gallium oxide has 5 phases. So it is called polymorphism. So this is again very particular to this gallium oxide material. So although out of these 5 phases, this beta phase, which is, so these phases are actually decided by the crystal structure it takes. So while synthesizing, you may end up in getting alpha, sometime beta, sometime gamma or delta. So again, depending on the process parameters when developing this material, you may get different phases. And these phases are decided primarily by the crystal structure it is attaining finally after the synthesis. So most stable, or if we just simply heat up the other phase of gallium oxide, it will finally get stable to beta phase. So beta phase is essentially monoclinic structure, and which we are typically using to realize all these devices. So then looking into the application of this particular material, that is gallium oxide, so it has a broad range of application, starting from the radiation detector. This is very important for space application. Then obviously there is this high temperature gas sensors, which was covered in the first day's session in this particular workshop. Then of course this we can realize power devices and deep UV photo detector, and we'll so these two application we'll try to see in detail. So now for the material development, so they are typically this can be done in 2 ways. One is the bulk growth. Bulk growth means the substrate and the device active layer all are made of same material. So that is called bulk growth or the bulk material development. And for that, this gallium oxide has a 2 method. So that is floating zone technique and Jochowski technique. So apart from that, we can also integrate this gallium oxide on other material. So this is typical, this overall device structure here in this bulk growth will be made of gallium oxide. But in this foreign substrate or this gallium nitride, zinc oxide, silicon carbide, so here essentially we can integrate this gallium oxide with the other material. Remember, this integration is very important considering the maturity of the technology, cost and all other things, because see gallium, if I take a quick example, so if we try to get this gallium oxide substrate, the cost is very high. I think 10 millimeter by 15 millimeter substrate will cost you around 2 lakh. But if we can integrate this gallium oxide on silicon or sapphire, which are less cost material, so we can eventually get very low cost technology. So that is okay. Another important parameter. So one is the reducing this your technology, the cost to develop one technology, and another important importance of this selecting this foreign substrate is the thermal conductivity, because as I mentioned just in the previous slide, gallium oxide has poor thermal conductivity. So now if we can integrate this gallium oxide on let's say on silicon carbide, because silicon carbide has very high thermal conductivity, so essentially we can get a much cooler device at operating at very high voltage or high power. So that is the another way and another reason that we are utilizing this foreign substrate. But again, challenges are there. We cannot integrate this any material with any other material. So there are a lot of other things we need to consider. So if we consider how to develop this material, so there are typical different type of deposition system. So of in this this is called again heteroepitaxy. So where we have different type of materials integration, and we can do that. So we have typically molecular beam epitaxy or MB. So again, we also can get this MOCVD or metal organic chemical vapor deposition. So they are, this MOCVD is for your compound semiconductor. This is the most widely used considering the commercial viability, because MB is typically used for research purpose. So, but the problem with these two techniques is they are very expensive compared to others. So now if we look at other techniques, that is pulse laser deposition or PLD and sputtering, but the problem here is that when we will try to deposit this material, that is gallium oxide, on some other material like sapphire, so the uniformity, that uniformity means this thin film we are depositing, that is gallium oxide thin film on sapphire, there will be some problem regarding the uniformity, because see, let's say we are depositing on a 1 inch square sample. So on one end we'll get some device performance, and another end we may get some different device performance. But considering the overall yield of a particular technology, we cannot consider this non-uniform thin film. So another few techniques which is used for this gallium oxide is mist CVD. So mist CVD is where essentially the precursor coming in the form of mist. So which is again a very emerging technique recently introduced by some Japanese scientists. So but this system is complex because the fluid dynamics inside the chamber is still people are working on. So now the last technique which again we are trying to utilize, that is low pressure chemical vapor deposition. So the advantages of this system is it is a low cost, of course, and then we can get high growth rate. Why this high growth rate is important? Because then we can quickly grow a particular device structure, and overall the yield of this technology will be higher compared to others. So now this is a typical schematic of the LPCVD system that we have developed. So here to deposit our this gallium oxide, we are utilizing this oxygen as precursor, and we are keeping this gallium as a metal. So and then this argon gas we are utilizing as a carrier gas. So you can see here inside this furnace on a board we are keeping our substrate, and then below this substrate we are keeping this gallium metal. Now when we'll flow this oxygen with the help of this argon, so then eventually we'll get this gallium oxide deposition on the substrate. So these are the typical process flow we are utilizing when optimizing this gallium oxide thin film on sapphire substrate, and this is the temperature profile that we are using. So this is the complete system. Again, this is a complete homemade setup so that we could develop. So now after developing this system, now we try to deposit this material, and then we need to characterize this material. So why first our purpose is to confirm whether we are getting gallium oxide or not, and then if we are getting gallium oxide, how about its quality. So now looking into, so this is the XRD plot or X-ray diffraction results. So from here, first of all, we can confirm that we are getting this gallium oxide material, and then from this sharp peak, we can also confirm that the quality of this gallium oxide is very high, because although there are 4 peaks, again this is a sapphire peak. That sapphire means this is a substrate peak, and these 3 peaks are essentially the parallel planes. You can see this is a 201, 402, and 603. So we could get good quality, good crystalline quality of gallium oxide, and which has this monoclinic structure, that is essentially your beta phase. Now after confirming this crystallinity, then our next aim is to confirm whether that surface is proper to fabricate device or not, because unless and until we get a proper smooth surface, we may not be able to get good adhesion of our metal contacts, and other problems may appear, like this interface or other problems may come. So considering that we could get reasonably well surface morphology, and then this is the XPS data which confirms the ratio of this gallium and oxygen. So why this is important? Because you can see this is a compound semiconductor where we have both gallium atom as well as oxygen atom, and this is essentially Ga2, 2 gallium atom and 3 oxygen atom. So whether we are getting this gallium oxide proportionally to this beta phase or not, so for that we need this XPS. Otherwise we may end up in getting different other molecules, so which we have we could observe initially. So after that initial optimization, we tried to understand the surface morphology, because I mentioned this surface is very critical when we'll go for the device fabrication. Now when we, so here we can see that you can see that we have simply tried to increase the gallium metal considered inside the board. So when we are increasing this gallium metal, we can see there is some slight change in the surface morphology, although we are getting thin film. But when we increase this gallium amount, so this is a gallium 2 milligram, 5 milligram, these are the amount of gallium we are considering inside the board. So now when we increase this gallium to 25 milligram, 40 milligram, you can see there are different nanostructure kind of thing is appearing on the surface. That means this is not good for typical power device purpose. But again, we'll show finally this material, this nanostructure may be suitable for other purposes. So may be suitable for some detection purpose. So we'll show this. So the take home message is that, so by changing this gallium metal inside the board, we can get material which is suitable for power device or typical electronic devices, and again we can get materials which is suitable for sensor or detectors application for optoelectronics or sensor electronics. So everything we can utilize based on the application. Now next we have tried to understand if there is any impact on the crystal quality when increasing this gallium metal. So but we could not observe as such change in the XRD peak, but there is a change in the crystallite. So this crystallite size, we are simply we have followed this equation, and from that we have tried to see how this crystallite size is changing with the amount of gallium we are considering. So then again here you can see, like when we are considering the low amount of gallium, we were getting this thin film, but with the high amount of gallium, we ended up in realizing nanostructure. Now, what is the basic growth mechanism? Because we should remember to establish certain technology, we need to confirm the science behind this. That is because we cannot just say these are the process parameter we have utilized and finally we got this. But we need to understand why we have got those observations. So then we have also tried to see the different optical parameters. So this is the UV visible spectroscopy. From here you can see there is a sharp cutoff around 274 nanometer, and from where we could calculate this band gap of this gallium oxide, which is around 4.76 electron volt. And there is also a variation in the band gap when we have changed the gallium metal concentration. So this is perhaps due to those nanostructures forming and the strain coming out from those nanostructure. So apart from this is typically for the band-to-band transition, we know, and this is the non-band-to-band transition. So we have observed from this PL result. So there are certain reasons also, like why there are those peaks at the UV range, blue range, green as well as red emission. So after that, we have tried to understand the quality of those nanostructure using this Raman spectroscopy. So now looking into the growth mechanism. So what is exactly happening with the increase in the gallium metal inside the pore? So first, this is some cartoon I am going to show and try to propose how these materials are getting deposited or getting different form. Once it is a thin film, another time it is a nanostructure. So first, this is the different type of metal, that means precursors are coming on the surface of this substrate, that is sapphire. So then this chemical reaction is happening on the surface, that is gallium with the oxygen. First it will form the Ga2O, and then Ga2O with the sufficient oxygen, it will form Ga2O3. So that is why I was saying that this XPS information is important to check the ratio of this gallium and oxygen atoms. So then after the deposition of this initial adatoms, it is forming some island kind of this structure on the surface. With the further deposition, this is turning into this thin film. So this is typically called layer plus island growth, because in this epitaxial growth there are typically three growth mechanism or growth model we have. So where we can also get layer by layer growth, or from first place we can get island growth, and then we can also get this layer plus island growth. So this is also named after the scientist who modeled this growth, which is Transky-Krasnov growth model. And after increasing more gallium inside this metal, so there could be this gas-based reaction with the saturation of this Ga2O vapor, and there could be this vapor solid growth, and we may end up in realizing this kind of nanostructure. Now if we keep on increasing this gallium metal further, so how these nanostructures are coming, so it could be due to the accumulation of gallium. Again, remember this gallium melting point is very low. I think it is of the order of 39 or 29. So now due to that, there is a high vapor pressure inside the furnace, and we have this vapor liquid solid growth, and which essentially gives us this nanowire kind of structure. So now we can establish that how to change this gallium metal inside the board, and how to get different type of structure, like not only nanostructure, how can we get this nanowire, or how can we get this thin film. Because now changing this gallium metal we can fabricate, or we can go ahead with the different material application for the different devices. So next, after synthesizing this good crystal quality gallium oxide to enable or to use this material for any electronic device purpose, we need to dope it. Because as I mentioned initially, this before this 20 years or 30 years back, these oxide materials, or this particularly this gallium oxide, this wide band gap or ultra wide band gap semiconductor, was treated as an insulator, because that time people could not dope it. Now, because again we need to dope it, because we need to change the conductivity. Now, what are the dopants available? So these are the typical N-type dopant for gallium oxide. Again, you know that depending on the material, the dopant changes, because we know that in case of silicon, the arsenic phosphorus gives us N-type, whereas boron gives us the P-type material in case of silicon technology. But in case of gallium oxide, you can clearly see that SN, silicon, germanium, these are commonly used for N-type material, and for P-type there is a magnesium, zinc, and this nitrogen. Another thing, just I would like to share that after confirming the material quality, we need to check the electrical conductivity. So we try to, so typically Hall measurement is used to check the material electrical parameters of this material. So after without doping this gallium oxide, we could not get any electrical parameter. That means those gallium oxide material without doping, it is not at all useful for fabricating any electronic device. So this is the message. So now we need to dope it, and we tried to dope this gallium oxide using tin. But here there is another trick. So this P-type gallium oxide, people propose this material by theoretical study, but still very few people reported this P-type gallium oxide. Why? The reason is, again, if you go back to the theory, this is the band structure. So band structure of gallium oxide. So here you can see this is the conduction band again, and this is the valence band. And again, you know that this curvature of this conduction band and valence band actually decides the whole electron effective mass as well as hole effective mass respectively. Now you can see that this curvature of this valence band is almost flat. There is no curvature in this valence band. So that means even if we can get some P hole or the P-type gallium oxide, but the effective mass will be very high because there is no curvature. So effective mass is very high. That means even if we have holes inside the gallium oxide, they may not be able to move. So that means we will not get any conductivity due to the holes inside the gallium oxide. So this is the theory. And perhaps due to that, people still struggling to get the P-type gallium oxide. And although like N-type gallium oxide people have achieved, and we have also achieved this. But another thing from the device perspective is that we need NP junction or PN junction to get the best possible breakdown voltage. We'll see this again in power device breakdown voltage is one important parameter. But since we do not have any P-type gallium oxide, we need to utilize some other P-type material like P-type gallium nitride. On top of this, we can deposit N-type gallium oxide, and then we can get heterojunction PN junction diode. So hetero, not homojunction PN junction diode like your silicon. So these are the things we can do. Now we have, as I mentioned, that we have tried to dope this gallium oxide with the tin. Again, we had to change the configuration. So here you can see this is inside the furnace. So where we have kept the substrate inside over a board and kept the other tin and gallium, two precursor, just 8 centimeter apart from that on substrate. And then we have maintained this 1050 degree centigrade temperature under the gas flow. So these are the other process parameters which have utilized. But when we try to dope this gallium oxide with the tin, so initially we ended up in getting alloy, SN alloyed gallium oxide. So doping, again remember, doping is not alloying. Doping, again, you know that typically in any material, so you'll find 10 to the power 22 atoms per centimeter cube, and dopant atoms should be 10 to the power 17 or 18. But alloyed means, so there are almost equal portion of atoms. So alloying is not doping. So in case of electronic application, obviously. So initially, when we tried to dope this gallium oxide with the tin, we ended up in getting SnO2 as well as SN alloyed gallium oxide, not the doped gallium oxide. So how we confirm this phenomena? So here you can see there is a peak shift in the gallium oxide. See, this red color is the after incorporating tin. So which and this blue color is the gallium oxide peak, and there is a peak shift. So this peak shift means that the lattice, this distance, everything got changed. So that is why we could confirm that this is alloyed. This is not gallium oxide, which we intended to. And another problem we faced, you can see from here that we got nanostructure, not the thin film, after doping with the SN initially with these all parameters. So, but our purpose is to get the power device, but and then we need thin film for that. We cannot go with the nanostructure. So we kept on trying these different other techniques, like same precursor, but we kept on changing this different process parameter, that is time, distance, then your temperature, gas flow, etc. So after doing that, what we have observed that this at a certain distance. So here we have actually changed this tin concentration. So earlier we kept this is 40 milligram of tin. Here we are considering 10 milligram of tin along with the 100 milligram of gallium. So then we could see a trend towards thin film, but still there are texture. So it is not that, it is still not very useful to get power device, because we need a very smooth surface to realize power device. Again, then we tried to increase this tin composition along with the gallium, same material gallium. So we could observe that this trench-like structure and this the holes inside the structure is getting reduced, but still we could not get a good quality thin film. Although from the XRD plot, we could confirm that it is not forming alloy. So this is the XRD after changing those process parameter. So here here we could not see any alloyed gallium oxide or any SnO2. So then we can now confirm that we have now SN doped gallium oxide, not SN alloyed or SnO2. So these are the band gap variation after incorporating this gallium oxide, tin on gallium oxide, and then this is the SN atomic percentage change. So here also you can see after certain in tin concentration, the incorporation is getting saturated. So we cannot keep on increasing this tin incorporation inside this gallium oxide with just simply increasing that considered tin. So these are the difficulties. So this is again the PL plot, how the different peaks are shifting with the incorporation of tin. And good news is here, so we could get the Hall results. That means we could now contact this thin film or the material with the metallization, and here you can see we could achieve maximum 10 centimeter square per voltage second of this mobility. So because these electrical parameters, this is a typical workflow when developing any device. We need to confirm or optimize our electrical parameters after synthesizing any material before moving towards the fabrication of devices. So here we could get reasonably well electrical parameters from the grown or doped gallium oxide. So after confirming that acid doped gallium oxide on sapphire. So again, remember all the deposition here we did on sapphire, that is a substrate. So then, as I mentioned initially also, so instead of sapphire, if we can go with, or if we can utilize silicon, that could be the best possible thing. Why? Because silicon is the most, again, like existing electronics, mostly you will see the silicon. So this gallium oxide based devices, you can integrate on silicon and get the much more enhanced performance from your overall system. So this integration is the most desired integration, but there is a difficulty. So you can see when we try to deposit this gallium oxide on p-type silicon, again this is another thing that also I have mentioned, because if we can get good quality n-type gallium oxide on p-type silicon, then eventually we can realize p-n junction also. So, but we could not get thin film. So, in case of gallium oxide on silicon, and the possible reason is the silicon dioxide on silicon, because with the configuration, with this LPCVD configuration we utilized, it is not possible to get rid of this silicon oxide, which is perhaps possible in ultra high vacuum system like MB. Because if we know that if we heat up this silicon, and again there is oxygen, another precursor, when depositing gallium oxide, we'll get this silicon dioxide, and silicon dioxide is an amorphous material. So on top of any amorphous material, if we try to deposit another material, we'll always get this amorphous or non-crystalline material. So another possible reason for this kind of nanostructure on silicon could be due to this high lattice mismatch, because when we'll try to integrate one material with the another, so two parameters is important. So one is the lattice mismatch. Lattice mismatch is essentially the atomic distance in a particular material, and another one is the thermal expansion coefficient mismatch. So how fast or how slowly the distance between two atoms is reducing and increasing. There should not be any mismatch. So then again you will end up in defective material after synthesizing. Now after depositing on silicon, we also tried to utilize this gallium nitride. Gallium nitride is another mature compound semiconductor technology after silicon. So, but initially we got again nanostructure, but slowly after optimizing different process parameter, we could get somewhat thin film. So you can see how the surface morphology is changing with the different process parameters, that is gallium metal considered, as well as the temperature. So this is the best possible surface we could get with the 8.9 milligram of gallium under 925 degrees centigrade temperature. So this is again the confirmation of this crystal quality of this gallium oxide grown on n-type gallium nitride. Now once again we tried to deposit this gallium oxide on p-type gallium nitride, because again to realize p-n junction we need p-type substrate material. So earlier it was n-type gallium nitride. So here also we could get good quality gallium oxide on p-type gallium nitride. So you can see from this FSM, cross-sectional FSM, as well as from this XRD. Now this is up to this we explained how we have developed the gallium oxide nanostructure, gallium oxide thin film, and doped gallium oxide. Now we are ready to go with the device fabrication. And for the device, as I mentioned, we have two broad application. One is the power electronics application, another one is the optoelectronics application. So what we do in the power electronics application, so this is a typical power electronics system. So we know that essentially this power electronics system is to condition different form of power. So this is input power, and then we'll get the conditioned output power with the control topology, and now this power converter is the heart of any power electronic system, and inside this power converter you will find some solid state devices, and those devices are operated either as a linear device or as a switching device. So this actually these devices are also called power devices because the application is power electronics, and which is typically the voltage current level is way high than the microelectronics. So now what is the problem? Now when converting on one form of power, so DC, you know that AC to DC, DC to AC, AC, DC, DC. So these are the different form of conversion. So when converting one form of power to another form, we should ensure the efficiency. So there we should not lose any power just for confirming one form to another. So what are the main causes for this losses? So there are typically two losses when we are utilizing this solid state device or power devices as a switching device. So they are conduction losses and switching losses. And what are the conduction losses? The on state loss and off state loss. So now again, you know, ideally in a switch the losses should be zero when it is in on state. So exactly there should not be any resistance, so there should not be any voltage drop across your device, so only the infinite amount of current should flow, like this is the ideal case. Then again, when your switch is turned off, there should not be any leakage current. But again, finally, these are all ideal situation, will always end up in getting some losses. Now the main purpose in this power device research is how to reduce all these losses and increase the overall efficiency of our power electronic system. Now this is another important three-dimensional plot for your power device. You can see this is power device. So okay, it is understood that we need to operate our device at very high voltage as well as very high current. So now look at this voltage rating. So this is of the order of 10 kilovolt or 10,000 volt, and the current is also of the order of 1000 ampere or 100 amperes. And remember, in microelectronics our current goes up to milliampere, not even ampere. And the voltage level, again, you know that less than 10 volt or 20 volt. So but in this but in case of power electronic application, our device needs to sustain all this high voltage and the current. And another interesting requirement from our power device is the frequency. So you can see this is the like 100 hertz, then kilohertz, then megahertz. So according to this frequency, actually these are different devices or different power devices. So the first one is the thyristor. So then we have this gate turn off transistor, GTO, then IGBT, insulated gate bipolar transistor, then MOSFET. So this is all silicon based technology. So these all devices are made of silicon. So another interesting thing is this is the way our year advanced. So that means the thyristor is the oldest power device, and the MOSFET is the most recent power device. So with the year, our power device, in case of power device, we intend to operate our devices at very high frequency. These are power devices, high voltage, high current, fine. But why we need to operate our devices at high frequency? Because see, at high frequency, because again this is the power converter, and along with the power device there are a lot of other associated components like different inductors, capacitor. So now if we operate our overall this power electronic circuit at very high frequency, all the other associated component size will reduce. Remember, the size will reduce, so our this overall power electronic system will be more compact. Yes.
हाँ इसलिए मैं यहाँ पे आ गई.
Sorry.
Okay, हाँ मुझे चलेगा. हाँ हाँ.
Can you please mute yourself if I think someone is speaking? Okay. So so if we can operate our power electronic system or our power devices at very high frequency, so then the other associated component size will reduce and their efficiency will increase. So with the increase in the frequency, we get two advantages. One is the efficiency, that means the all these losses will be less, and another one is this cost. So because size, if our power electronic size is getting reduced, overall material cost and again production cost will reduce. So again, I think efficiency and the cost are always the main driving factor for our engineering research. So with the high frequency, we can do that, high frequency power devices. So these are again some power device related benchmarking chart based on resistance. This on resistance provides us the on state losses, and breakdown voltage we can gauge the off state losses. So again, here we can see just if we, so this is the most desired corner. Why this is the most desired corner? So at this corner, our device will operate very high voltage, like it can sustain very high breakdown voltage, but at very low on resistance. That means at very low on state losses. So now if we can see the different material trend, so this here is the silicon. So but if we leave the silicon and go ahead with the other wide bandgap semiconductor, you know that gallium arsenide has 1.43 electron volt of band gap, then silicon carbide, then GaN and gallium oxide. So ideally with these wider band gap semiconductors, we can reach to these ideal corners, which is our goal for realizing our power devices. That is why this is another motivation why we are operating or using gallium oxide. So there is another obviously thing, this is diamond. Again, diamond, you know, it has other problems associated. So having said that, so initially, we tried to realize this two-terminal device, that is simple Schottky barrier diode. Here you can see that this is a beta gallium oxide on sapphire, which has a relatively good surface. This is the AFM result, and then we have realized this Schottky barrier diode. So this is the platinum contact, which is essentially giving the Schottky contact, and this is the titanium gold contact, which is providing us the ohmic contact. And these are the some other device results. So after that initial confirmation of device result, because see, when you will try to achieve any diode characteristics, that means essentially non-linear characteristics, you may not be able to achieve that, because there are all other problems associated with that. So after confirming that we are getting relatively good diode performance, we tried to see whether these diodes are applicable for high temperature operation or not. So in that regard also, we could see that this diode is giving us a stable performance, and more importantly, this is the switching performance. So this figure provides us, this is when our switch is going from on state to off state, and when moving from on state to off state, there is a possibility of losses. That is a switching loss. And again, here we can see with the increment in the temperature, there is no change in this current with the time. That means with there is no switching loss change with the temperature. So this is the another interesting result we could find out. And then further, as we have developed this gallium oxide on p-type silicon, we tried to see whether we are getting a diode behavior or not. So we could get diode behavior, but this one I would say is not the best diode behavior we can achieve using this silicon. Again, silicon, we have already observed that there is a problem of developing or getting thin film for these devices. So this is another device result or power device result. This is the material which we developed on p-type gallium nitride, but here we could get very good power device performance. So you can see here, this is the reverse bias, and this is the forward bias characteristics, and the on-state voltage is typically 3 volt, and the order of rectification is 10 to the power 4, which is reasonably well power device performance. And another interesting thing is that, because see, why we are doing this heteroepitaxy, it is clear, because we do not have p-type gallium oxide, so that we can get best performing PN gallium oxide diode. So that is why we need to move with this heterojunction, that is gallium nitride. So people have tried different other techniques like mechanical exfoliation or transfer. So this is something, another interesting thing of gallium oxide, because gallium oxide as like graphene, you can exfoliate, because the C-axis, you have seen that in case of monoclinic structure, it has A, B and C, that is the lattice constant. In the C, lattice constant is relatively high. So essentially we can just peel out one layer of gallium oxide. So people have tried that also, and with that they have tried to realize this kind of heterojunction diode, but obviously this kind of peel off technique is not suitable for industrial scale up. So there, this kind of LPCVD technique can help us. So moving ahead, so there is some optoelectronics devices we could develop. So here we mostly try to develop this photodetector, so which operates at the deep UV region. So this is the commercially available packaged photodetector. And what is a photodetector? So essentially this is a photosensitive material on the substrate, and now if we illuminate this with the lamp, then there will be some electron hole pair generation. And now if we metallize this photosensitive material and apply some bias, those generated electron hole pair under this illumination, we can separate out and we can get the conductivity. Now this is the band diagram to represent this phenomena, and here our interesting interested region is the UV region, and which is just before the visible region in terms of wavelength. And out of this UV, there are three regions, that is UVC, UVB, UVA. So most importantly, we are working on this UVC, which is the most dangerous ray. And again, you know that due to the hole in the ozone layer, we may get this UVC coming from the sun, and which may cause cancer or the skin cancer. So sensor or that photodetector operating in this range of UV is very important to know the ozone hole layer condition or other things. So to realize any photodetector which will operate in this region of UV range. So here we can see in terms of band gap. So this is the simple formula here, as you know that this Eg is the band gap, is Planck's constant h multiplied by the speed of light divided by wavelength of operation. So when we calculate this and utilizing this UVC region wavelength, so this gallium oxide is very much suitable for this kind of UVC detector based on the its band gap. So now we have tried to realize some photodetector based on this SN alloyed gallium oxide, because again just recall that we have mentioned that although we could get initially this nanostructure, but like those are not suitable for thin film or power device operation, but they are suitable for the detector. Now these are our other detector performance, like considering the stability and the speed of these detectors, and like we could get very good performance from this detector. Then we have tried to understand the possible reason for that also. Just hold for a second, I think some noise is here. Okay, sorry for this interruption. So so then we have tried to utilize this SN doped gallium oxide along with this SnO2, and then we have tried to fabricate these photodetectors by fabricating IDE or internetized electrode. And here you can also see there is a huge photo to dark current ratio. PDCR essentially means photo to dark current ratio. So with illumination we are getting change in the current of the order of 90,000, so which is very high. And then also we could get reasonably well speed of these photodetectors, and then we try to understand the possible factors behind this high performance. And again, so most of these photodetectors efficiency is above 100%. So that means one photon is essentially giving us more than one electron hole pair. So we are still trying to understand what is exactly happening, and this is this. So with this, I'd like to conclude that in terms of material development, we could get this gallium oxide thin film as well as nanostructure. Then there are different reason behind this thin film nanorod or nanowire observation, which we have elaborated, and then we could dope this gallium oxide. Again, we realized both the doping as well as alloyed gallium oxide. So after that, we have realized this gallium oxide on different substrate such as N-type gallium nitride, P-type gallium nitride, as well as silicon. So then we have also tried to fabricate few devices. In case of power devices, we could get good diode performance with the decent J on and J off ratio. Then we have also realized detectors, photodetectors operating at the wavelength of 254 nanometer or UVC range, and we could get a very good responsivity or photo to dark current ratio, but the speed of these devices are still slow. So these are the challenges we need to work on in future. So with this, I would like to acknowledge my students, because essentially these are all the students' work which I am showing. So the first Arnab, first one, he is actually developing all this material to fabricate both power device and photodetectors. Then Ashish already graduated on photodetector using this nanostructure. Then Manoj in Arpit is performing his work on power devices. So then I would also like to acknowledge my collaborator, Professor Chi, and at NCU Taiwan, and I acknowledge the funding support I received from various agencies such as IIT Guwahati, then MHRD, DST, IIT Mandi, as well as the Spark. So with this, thank you, and I would like to take questions if you have. Yeah, thank you.
Thank you, sir, for this well-versed presentation and a highly beneficial talk. We can now have the questions. So the first question asked by Ramesh Babu is, in the XRD studies, why are the planes negative?
Okay, that is not negative. That is not negative. So that is a bar. Okay, so that is not negative. That is minus, not minus, that is a bar. That is not negative. Okay. So typically, I think, okay, I guess here. So they are typically the crystal planes. You know, this is the reciprocal plane. So this is again, if you look at the this overall crystal plane. So then these are not negative. So these are all, sometimes this is represented by dot also. It's like you will find some dots. So these are all just opposite plane. So you know, in reciprocal space map, it will be easier to show you. So they are not negative, just opposite of two. Okay, these are all planes. Okay. And I do not have actually a good picture to represent or to elaborate this. I need reciprocal space. Okay. So this is the typical planes, you can say.
Okay. Okay, sir. So the next question asked by him is, why is the beta phase stable? And if you can please tell about the different phases like alpha, beta, and so on.
Why the beta phase is more stable? Yeah. So the
Yes,
question is, can I find this? So why the beta phase is more stable? Okay, so I think again from crystal point of view, so first of all, I would say I am not the correct person to answer this. So these are some material properties. So if we heat up,
you also don't know.
if we heat up this material, eventually we'll get this monoclinic structure, and that monoclinic structure is the most stable one. I guess some thermodynamic rules is there, so which decides which material crystal structure will be stable. So that is why perhaps the other phases like alpha phase or gamma phase, they are not stable. So this is from thermodynamics point of view what I can say.
Okay, sir. So the next question is, If you can please suggest any mathematical model for polymer Schottky diode.
Polymer Schottky diode. Again, I have not worked on these polymers, but obviously I think the behavior from polymers or the theory behind this polymer diode will not be same as this inorganic material. So, but I exactly don't know like how to model this. Okay, so the suggestion would be see diode again. You know that typical this Poisson's equation and other things you need to ensure, but for polymers, how the carriers are coming, that you need to check. So there, like I think the physics behind this is altogether different than the inorganic material. So I don't know exactly, but you need to approach in this way, like how the carriers are coming, then how the electric field is being generated, and that you need to check. Yeah.
The next question asked by Dr. Venkaya is if you can please elaborate the simulation model for the photodetectors.
Simulation. See, again, I have not done any simulation because one thing I must say here, because you have seen that in case of photodetector, there are a lot of nanostructures. So nanostructures, again, they are not controlled, like they are very random, and there are many defects also. So now all this randomness or this variation to model in a like in a mathematical model to check all these things is, I think, would be very difficult. But people are trying. There are few standards model, but my take on this would be that modeling this photodetectors. This photodetectors means this emerging material based photodetectors will be very challenging, because silicon photodetector, if you want to model, I think it is already been done, so it is there. But yeah, there are a lot of challenges because this material itself is not very mature. So now to model this device behavior would be very difficult. Yeah, I think if this answers your question.
Thank you, sir. Due to time constraint, we will move forward and the rest of the questions will be answered in the chat box. Thank you, sir, for answering all the questions and for your precious time. Over to you, Johar.
Thanks, Niharika. The next speaker of the day is Professor Roy P. Piley. Roy P. Piley is a professor and head of the Department of Electronics and Electrical Engineering, IIT Guwahati. He has earned his PhD from IIT Madras, and later on he joined IIT Guwahati. He also served as head of the center in the Center for Nanotechnology from 2013 to 2018. He has more than 90 publications in national and international journals and more than 110 conference proceedings, has written various book chapters and filed 3 Indian patents and 1 international patent. Professor Roy is a recipient of several awards, few of those from Google, Samsung and IBM India. He is a senior member of IEEE, line member of IETE, member of IEEES and member of VLSI Society of India. He has implemented several projects of ISRO and Ministry of Electronics and Information Technology, Government of India. Professor Roy has organized various workshops and conferences and has taken many responsibilities in both academics and administration. He has guided more than 15 doctoral students, has inspired thousands of young engineers and technologists through his majestic personality and core application-oriented research activities. His area of research are microelectromechanical systems, VLSI circuit and system design, nanofabrication and semiconductor devices. Now I would like to invite Professor Roy P. Piley and request him to kindly share his invaluable insights on the topic of fabrication and characterization of field effect transistor based detection of glutathione. I am requesting Professor Roy to take over this session. Sir, please proceed, sir.
Good morning to all of you. Thank you for the kind introduction and this opportunity to give you a talk. Please let me know. It is 1 hour talk, no? 1 hour, no?
Yes, sir. Yes, sir.
Thank you. Thank you. Thank you. So let me share my screen. Okay,
yes,
so
sir.
I hope I am audible enough and you can see my screen.
Yes, sir. Slides are clearly visible and audio is quite clear, sir. You can
Thank you
proceed,
very much. Yeah, thank you. So just wanted to tell the participants that, if you have a doubt in the middle, or if you want me to repeat some concept, or if you have a quick question, you can interrupt me in the middle also. We will not spend much time. We will shift most of the questions to the last. But if you have a quick thing, we will respond. So please feel free to interrupt me. I cannot see you if you raise hand, but you have to unmute and speak. Okay. So the first of all, I just want to acknowledge my teachers. Whatever I know today is taught. Somebody taught me. Either my teachers taught me or my students taught me. These are my PhD students, passed out about to pass out. And this work is today's research work is done by Ujjwal Burman. He was a PhD student in the Center for Nanotechnology. So this is their work basically. So now I just want to briefly organize my work into 3 parts. One is I believe many of you are electronic students or physics students, but not all of you. So I just want to give a very brief introduction about MOS transistor. That is the most famous device. We could call it as a nano device because of the dimensions, the dimensions of MOSFET. Not all dimensions, some of the dimensions in a MOSFET is nanoscale. And I also just want to, even though we will be discussing one research example, that is FET fabricated for cancer detection. But biosensor is a very wide area, as you are aware, but I just want to briefly present that also. What all areas one can work in, and I want to encourage you that there are a lot of opportunities, a lot of things can be done depending on your background, and if you are a chemistry student or a biology student or an environmental person, a lot of things can be done. So I just want to bring into your notice. Okay, so it's sad that we could not talk this in person to person. Hope sometime the next workshop or some of the you will have a project in Inup, Iitg Guwahati, and you will come to campus and you will work in the campus and in the laboratories. So we hope we will physically meet soon. Okay, so this is probably others might have presented this similar slides. DNA, that is a long molecule helix structure, and which contains the unique genetic code we have. All the information regarding our development, functioning, growth, and reproduction are there in this tiny thing that is around 2 nanometer. So if you compare today's MOSFET dimension, that is also about channel length is about equivalent channel length is about people say 5 nanometer. Exact channel length is physically it is slightly bigger than that, but still that is how they characterize that. And also if you look at one of the antibody, IgG, this is a common antibody, and that dimension is around 10 nanometer. Virus, now we are living in a post-COVID kind of a situation. So we know a lot about virus, and that is about 50 nanometer. So red blood cells, what we are talking is about 10,000 nanometers. So these are the kind of dimensions we are talking about our devices. Okay, so this is a very preliminary high school kind of a slide which want to tell you that okay, anything you have, I mean, you have a, I mean, mobile phone, you have a USB, or you have a nowadays camera is in mobile phone only, or you have a laptop. So all these things really need electronics, and which means that you need electronic devices. So you know, in all these devices, what you have common is MOSFET. You have a lot of MOSFETs in this, all these devices, all these structure, all these systems. So we want to just go back a little bit. It's a very brief history. You know, I mean, the things, the development of the transistors started very long time back, more than 100 years back. In fact, almost 115 years back. You know, Lee DeForest, he invented vacuum tubes. You know, vacuum triode. Triode means there are three terminals. That is why three contacts are there from the device. That is why it is called triode. You know what is the idea? Basically, the physics students, we have learned in high school that if you shine light with appropriate energy or wavelength, it can emit electrons. Or if you can heat the cathode, it can emit electrons. So these emitted electrons, you know, is collected in a terminal called anode, a plate called anode, where you know you apply positive bias. Since electrons have negative charges, you know this positive bias will attract these electrons to the positive plate, and if you keep a grid in the middle, it can be positive or negative bias. Probably it is negative bias. So what happens is you can control the flow of these electrons. So that is the basic idea. So cathode is a negative voltage you apply, and that is where the source of electrons. Finally, electrons are collected here. The number of electrons collected basically can be controlled by this third electrode grid. So that is basically the mechanism of a transistor 100 years back. Surprisingly, you can see that the same mechanism happens today also. I mean, there is a source, and there is a place where electrons are collected, and there is a way in which the flow is controlled. So, I mean, the ideas are same only. So, we are working on one of the old ideas. So, but you know, I mean, people know, I mean, human beings know, they are very good, I mean, in the sense, you develop a concept, you try to find an application for that. So, by 1946, you know, using these vacuum tubes, people made a computer. I mean, and you know, the size of this room is quite big, and it need something like a kilowatt, many kilowatts of power, a separate, you know, electricity. I mean, separate transformer and EV station is required to operate this. But still, people tried. I mean, you know, I mean, how to make computers. Today, you know, in your tablet and in your mobile phone, much higher performance, extremely low power consumption calculators are there. I mean, but whatever it is, this is the beginning. You know, I mean, beginnings are important. History is important. So, first computer ENIAC in 1946. They were big size, huge power, short lifetime. No, I mean, this entire thing is in a vacuum. I mean, they create a vacuum and close it with glass, sealed glass. So this engineer's nightmare. Every day he will come to the computer room thinking how many triodes I need to replace. You know, it was very difficult. So compared to that, today, if you look at it, our devices are solid state devices. Solid state devices mean there is no vacuum and all. There is no glass ceiling and all required. So basically. Is there a question or anything? I mean, yeah, somebody is, yeah, maybe please check it whether everybody is I don't know, I can unmute him or you can mute the participant. Thank you. So basically, solid state devices, from the name itself, it's a solid material. All the source and drain and gate, everything is solid. So that is the basic idea. So this is a solid state device, MOSFET. Yeah. So this is another interesting aspect, since you are research scholars and all, I want to highlight that, the importance of making a patent and also the importance of theoretically predicting that you can make a device. This is a theory. This is not an experimental result. But the first MOSFET predicted, the operation was predicted by this patent, Julian Lilienfeld. He filed a patent in 1928. He called it as a device for controlling electric current. So basically he gave the explanation, there is a source and drain, there is a gate and all. He suggested some material and all. It was not fabricated, it was theoretical. He thought it would work based on some experimental result which were available that time. But the first transistor fabricated, any idea? After this, another 30 years it took to make the first transistor. The fabrication of the first MOSFET happened after 30 years of that. No, it is not that the people tried fabricating after 30 years. All the 30 years they were trying to fabricate a MOSFET, but it was not successful. The successful MOSFET happened after 30 years of this filing pattern. But in the middle, much before 30 years later, before that, after something like 20 years later, they fabricated BJT. The patent was for MOSFET, but when they were doing some experiment, by accidentally they discovered this BJT. These people, all of you must be knowing, Bardeen, Bratton and Shockley, they were awarded 1947, I think later, Nobel Prize for their discovery of this BJT. This was germanium metal and they were inserting some needles and all, and actually if you want to really fabricate a BJT, there are a lot of things. If you are a physics person or electronics person, you know that the base and all should be very narrow and all those things, and the doping should be correct and all those things are there, but they did not know everything at that time, but this was an accidental discovery. But as I told you, people, once they make something, people think what next can be done, where it can be applied, how can we improve it, what way we can think ahead, what future things can be thought about. That is one of the important characteristics. As a research scholar, you also would think about that. You got something working and you think about how to improve it and how to make a system and how to make a practical application. This is the way you also should think. So, the integrated circuit concept, they used BJTs earlier. Nowadays, we are not using BJTs much. We are using MOSFETs only. But they used BJTs, two BJTs they connected in the single substrate. That time wire was outside. Later on, but that concept was very important. Later wire also, if nowadays, in an integrated circuit, you make something like 1 billion transistors. You think about connecting all these 1 billion transistors. If you use copper wires, you need tons of wires, and you also need a very big room, like very big room to actually hold that wire. So, but such wires are not needed. We need many kilometers of wire in an integrated circuit, but basically these wire dimensions are very small. It is part of the silicon substrate. It is not silicon, it is a metal, but you will deposit metal and you will connect all these devices. One device have 3 to 4 terminals, BJT has 3 terminals and MOSFET has 4 terminals. So connecting all these 1 billion transistors, a lot of connections are required. So, that way, this idea, you can connect transistors, you can connect wires was very revolutionary, and that is how integrated circuit or chips have come up. So if I look at briefly, in first generation devices were vacuum tubes. The dimensions, if you notice, they are around 15 centimeter long and 5 centimeter diameter. Then these devices came. I mean, if you have done a lab, electronics lab, you might have come across these devices. Now also in our undergraduate program, the students are going to come next week, and they are going to do lab using these transistors, second generation. The third generation devices is basically NOR gates, AND gates, and things like that. And they have typically 100 to 1000 transistors per chip. But the fourth generation, your memory and all, your RAM and ROM and things like that. Nowadays you use probably DDR4. That's what I think. Maybe I don't know whether anything came up afterwards. Of course, nowadays people are moving to solid state memories also. But anyhow, these are some of the earlier ones had something like 1000 transistors, and this is something megabits. Not nowadays you have a lot of gigabits is available. So yeah. So now this is the fifth generation. I mean your i7 is your processor and all is much later, but there is something called the fifth generation, 1 million transistor. But where it will go? Tomorrow it is going to be device dimensions will keep reducing, and they are planning to diversify. I mean, earlier devices and metals were integrated. Now they are thinking of integrating some of the analog RF components and passive devices, power devices, sensors and actuators, biochips. So they are planning to integrate all those things in the same IC. That is the plan. So, I mean, devices will keep reducing. That is something called Moore miniaturization will go. More than Moore, I mean, Moore is a person, Golden Moore. I mean, he predicted a law, which I will be describing soon. So, more than Moore diversification is happening. So, combining this both is what is the today's direction. So, just little bit about the size aspect, about the MOSFET. I mean, this information, most of this information 1900, if you look at it, it was 10 centimeter. If you look at it in 2000, the device dimensions were 100 nanometer. You know what is the reduction? In 100 years, the size reduced by 1 million times. That's a huge thing. There are many discoveries since Stone Age. For example, farming, rice farming is a technology development. Or making car is a technology development. But in no technology development, we have experienced such a tremendous reduction or improvement of performance. See, I'm not saying the rice size should be reduced. Probably rice size should be increased. Why not? Or if I sow 1 kg seed, I should get this many kgs of rice. That quantity should increase over the time, isn't it? That is not happening. That's what I'm saying. Or in the case of a car, again, car size, I'm not saying size of the car should be reduced. If it is reduced to nanometer, none of us can travel in that. So I'm not saying that. What I'm saying is the fuel efficiency, for example, per liter, how many kilometers it will run. That is not changed by 100 times. 1 million times, not 100 times. We are talking about 1 million times. So, such tremendous improvement of device performance, or such a tremendous reduction of device sizes or the technology is not happened in human history. So that way, this is a very unique kind of growth is what we are talking about. So, why people want to reduce the transistor size is mainly 2 to 3 reasons. 2 reasons are given here. One is if you reduce the dimension, the metal areas and the electrode areas and all will be reduced. And once you reduce the area, your high school physics, the capacitance will be lesser. Capacitance is proportional to the plate area. So that is what reason. The capacitance is very important. That decides the frequency of operation or the speed of operation. How fast signals can be traveled through that. I mean, why capacitance is the problem? Because you need to charge the capacitor, discharge the capacitor, and then only you will get the signals. I mean, so that way this capacitance is very important. So if you reduce the capacitance, you can operate, switch the transistors faster. That means you can increase the clock frequency, or you can increase the circuit operation speed or bandwidth, etc. So that is one reason. Another is if you make the sizes smaller, you can increase the number of transistors in the given chip area. So earlier they were making something like 10,000 transistors in 1 centimeter square area chip. But nowadays they are able to make 1 billion transistors in the same area. So there are a lot of transistors. So once you have a lot of transistors, you can do parallel processing. You can think about multiple cores, different cores for 64 cores or 48 cores or whatever it is. So many chips are available in one chip itself. So many processors are available in one chip itself. You can increase the functionality. There is another reason which I don't have a slide, I think. The main reason is, if you calculate the investment, if you do the scaling, the transistor cost reduces. I mean, you may doubt this aspect. You may think, no. For making the new lab, technology lab, you need a lot of money, and making transistors smaller is more involving and challenging. You are right. You are very correct. But finally, since you are making so many numbers, if you calculate the total investment by the number of transistors or by the number of chips you make, the price is reducing. I will tell you an example. For example, let me tell you an example with that. Typically for your i7 processor, are you able to see my screen?
Yes, sir.
Yeah, thank you. Typically, for your i7 processor, you were paying around 5,000 rupees. So let us say paisa. How many transistors are there? You're talking about something like 1 billion transistors. Million is 10 to the power 7, billion is 10 to the power 9. So if you calculate, 10 million transistors. So if you just calculate in 1 paisa, you will get something like how many transistors? This is how many? So 10 to the power 6, something like 1,000 or 5,000 or 2,000 transistor paisa. I mean 2,000 transistors for a paisa. For paisa. So that means what does it mean? I mean, one transistor cost is reducing. That's what it means. You can buy one paisa, you can buy 2,000 transistors. That is what it means. So that is another reason why this scaling is very important. If you look at the companies, I mean, there are many companies, major players. Nowadays, Samsung is leading. I mean, earlier Intel was leading. Then Texas Instrument. I mean, they make different things like CPUs, memories, DSPs, wireless products, and communication, mobile phones, and general suppliers like that. There are a lot of people. I mean, it's a huge industry. So now, if you look at this is the way the dimensions are reduced. One thing, if you notice, the sizes are reducing by some proportional way, something like 70% every year. Every technology node, every 2 years, the size is reduced by 70%. Exactly, if you look at it, it is 1 by root 2 times. So that much is the size reduction. Anyhow, but in order to reduce the sizes, it follows one rule, something called Moore's law for semiconductor. Every 2 years, every 18 months, the number of transistors doubles. So that kind of a rule is happening. So I can predict today, in 2035, what will be the number of transistors in a chip. I can predict it today because of this rule. So since there was a rule like this, it is easy to plan for tomorrow. I mean, you are a research scholar. You will be passing out in 2024, let us say. So your research should be relevant in another 10 years at least. That is